and then we'll. Okay, so you should have just heard the message that this meeting is being recorded, and you might have also gotten a pop-up that says if you'd like to continue to please click OK or whatever. Please go ahead and do that. I want to let you know that we are recording. So what I'd like to suggest is that we're going to go ahead and use the chat for discussion and for questions. I and Alex will be monitoring that to bring up your questions. So go ahead and I would recommend also leaving your video off just for bandwidth concerns, but also that way if you don't want to be recorded, you won't be recorded that way. So if you leave your video off and you leave your audio off, you won't be recorded at all. So you can still participate and not be recorded if you don't want to. So we'll go ahead and get started. Welcome everyone to MapTime Davis and to the Davis R Users Group workshop today. We've got a joint workshop session. My name is Michelle Tobias. I am the Geospatial Data Specialist at UC Davis Data Lab, and part of my job duties, part of my many job duties, is to help coordinate MapTime Davis and provide support to our other research and learning clusters, which Davis R Users Group is a part of that too. So welcome again to this joint session of MapTime Davis and Davis R Users Group. Let's see if I can advance the slide. There we go. So quick reminder, we're recording. So really quickly, a little intro to what MapTime Davis is if you're new. Maybe you're coming from the Davis R Users Group side of things, or you're just new to all of this in general. So MapTime Davis is literally time for making maps. It started in San Francisco with a group of folks who just didn't make a lot of maps in their day-to-day lives, even though they're geospatial folks, and just wanted more time. And so that's what this came out of, was a meetup about making maps and making time for making maps. And since then, it's kind of spread out around the country and around the world, and you'll find MapTime meetups in a lot of different places, especially in most major cities, but also some smaller cities like Davis. So this is coordinated by the UC Davis Data Lab's Spatial Science Research and Learning Cluster. I'll talk a little bit more about that in a second. But so no, this is something that comes from campus, but it also includes you. So how can you get involved? The same thing is true of Davis R Users Group. How can you get involved in these things? You can come to workshops and studios. So MapTime has not only workshops like today, but we also have this concept of studio where we'll alternate weeks with time for just group discussion and group learning. So keep an eye out for those. We'll have one next week, and I'll show you the schedule in a second. You can help plan. All of our research and learning clusters, MapTime and Davis R Users Group, always need more help. There's always a couple dedicated folks who make it happen, but I know from personal experience and also talking with some of the Davis R Users Group folks, both groups need more help. So step up, become a volunteer, help at a workshop. You can present a workshop. You can help facilitate discussions or work sessions. You can help us find folks to give workshops. So whatever you're comfortable doing, we can use the help. So definitely reach out to folks on both sides of this, both MapTime and Davis R Users Group. We are happy to have more help. In fact, I will encourage you to help more. We definitely can use it. We can't do these things indefinitely with just the few people that we've got working. So in terms of MapTime Davis, what we have coming up, a fairly full quarter with a little bit of break in the middle. So this week we're working on an R workshop, but next week we're going to have a discussion about the future of MapTime and how we can make it sustainable. So if you love MapTime, if this is useful for you, please come to this discussion. We've got to figure out how to get some more people involved in order to keep this thing going. I am sort of at my limit on the folks that I can pull in to do workshops. So if we want more workshops going forward and we want to make this sustainable, I'm going to need some help from all of you. And so definitely come to that next week, and we'll be advertising that more on the list. But after that, we're going to take a couple week break because we just had scheduling issues, and that's totally fine. But then on February 9th, I'm going to be giving a geocoding workshop. Specifically, we're going to be using QGIS, but I'll talk about some of the options in R as well. So if you've ever needed to work with address data and you need to turn that into points, come to that. Then we've got a studio the next week about again, working with address data, so more discussion and question and answer kind of session about address data. And then we've got the week after that, February 23rd, we've got folks coming from Esri to show us their new field collection tools. So if you're doing field work and you want to work with spatially enabled field data collection, that could be really helpful. And then the following week, the last week that we're going to have map time this quarter, March 2nd, we'll be talking about field data collection in general. So not just Esri products, but other tools that you could possibly use. So this is all on the Data Lab website, and on if you can search on there for spatial sciences and you'll find map time, or search for map time, that'll come up too. So with that, that's what I have for our intro. Today, I'm going to stop sharing my screen. Today we have Christian John, who is here to tell us, well, to give us a workshop about using R and Earth Engine. So I will let him take it away, but thank you very much for joining us. I'm really excited for this workshop.
Super, thanks a lot for having me, Michelle, and the rest of the Map Time regulars. So today we're going to be talking about basically going from raw data that exists out on the cloud that was created through like Landsat or Sentinel or some of the other satellite devices, and going from that to high definition images that you can use in presentations that aren't 50 megabytes large. And I don't know about many of you, but a lot of times when I want to create maps, I like to go from a raw data set to my finished product, because I can decide exactly what time frame of data I'm using and what spatial factors are going into it. But I frequently end up with presentations that are like 180 megabytes big, and I can't just email that to a collaborator or my advisor or anything. And a lot of stuff like that comes from unnecessarily high resolution data throughout your sort of data pipeline. So I'm going to go ahead and share my screen here. So let's see. If I'm not mistaken, you should be looking at a GitHub website with a map on it. Do people see that?
Yes.
Okay, super. So I'm going to use Yolo County as an example today, but there's going to be some free work time kind of in the middle of the discussion, so that you can figure out what region of interest you might be interested in working with, and you can sort of have some independence in what you're going to ultimately create today. So our major objectives for this workshop are to work toward understanding the relationship between what satellites see and what satellite data actually is and what we think satellites see. And then to navigate the sort of inverted coding approach of Earth Engine, which you'll understand in a minute, and then integrating both Google Earth Engine and R in a data pipeline. So before we get started, two things that are important. Number one, you need to have a Google Earth Engine account already. And if you don't, you are going to be a little bit bored for the first half of this presentation because you won't be able to code along. But if you go to the link, which I'm going to post in the chat here, this GitHub repository contains all of the code we'll use today, as well as all of the data that we will download. So if you don't have an Earth Engine account, you can directly download the data that will be produced in this pipeline and the intermediate steps. Let's see. Okay, and the ultimate goal is to create some high resolution imagery like this plot of Yolo County, or this massive California, or if you want to get creative and spend a little bit more time afterwards, you can even create these moving GIFs of sort of monthly composites of imagery, which this is also Yolo County. But before we start with actually getting data, I want to just have a brief intro to what the data actually are. So I posted another link from the Stack Exchange GIS page, because there's a really good discussion in here by Rodrigo Principe, which is a person that you'll find a lot on Earth Engine discussions on Stack Exchange. He's super helpful. And he has a really nice explanation for what the data that we're actually going to be working with is. So you have this sensor in space here, and that could be like Landsat, for example, and it takes a bunch of pictures of Earth. And you can think about pixels in an image the same way you think about your typical digital camera. And if any of you were born in the, I don't know, before 2005, you probably can remember a time when people were buying digital cameras purely based on the number of megapixels they contained. And these are basically counts of how many pixels you can get out of a single sensor in your camera. And the same sort of principle applies for satellite data too. They have these cameras that take pictures, and they have a certain number of pixels in the image. And depending on how high resolution it is, you can resolve different scales of like landforms and land cover and stuff like that on the ground. But a satellite is above the atmosphere. So there's a lot of factors that influence how it detects color of the actual Earth's surface below it. And so there's several sort of layers of processing that we need to go through in order to generate images that look like what we think Earth should look like. And conveniently, Earth Engine already has these processed data products available. So some people, depending on what they're doing, might want to use the raw data from the satellite, but some people want to deal with a correction where, okay, we're looking at this picture in the same capacity as like if you were right at the top of the atmosphere. But what I'm going to show you today is working with the surface reflectance product, which essentially this accounts for differences in the sun angle and atmospheric conditions. And so ultimately what we see as green in a picture will be green on the ground. Okay, so we are going to start out by working in the Earth Engine code editor. So you should be looking at my code editor right now, and you can see I have a ton of different folders of different projects that I work on. And within each of these folders, there's a bunch of different scripts that contain lots of different code for basically accessing, mapping, and processing and downloading data. So if you navigate to the GitHub page that I shared earlier, Alex, thanks for putting that link up. Under the scripts folder, there are a few getData.txt scripts, and we're going to be working with this getData_sr. And yes, Ellie, I can make it bigger. I think. Yeah. Okay, so here we're in my scripts subdirectory of the context maps repository. And here's a link to the script itself. And so you can directly copy and paste all of this code here, Command C, and over in your Earth Engine code editor, so it's code.earthengine.google.com, you can paste the code in there. Now, dealing with JavaScript is super different than what many of you might be familiar with in the sense of like R, because we use R interactively often, where we'll say, okay, library tidyverse, read.csv, myfile.csv. And then you can run each of those lines of code independently. But when we're working in the Earth Engine code editor, this, you kind of have to think about it as one cohesive body of code that's all run at once. And you can't like run this line 8 here and then run line 22. You have to compile everything together at once, and then you'll click this run button up here. And so I'm going to start off by running my script. And then I'll walk you through what's going on. So Earth Engine, and I'm not a JavaScript coder. I've learned JavaScript so that I could use Earth Engine, but from my experience working on here, there's a lot of sort of inverted philosophy in how we design our code for Earth Engine. So I start off by defining a region of interest, which I initial as RLI, and I use Yolo County And again, in several minutes, you'll have an opportunity to play around with this and choose your own region of interest. So you might use something else in the future. But you'll start off by defining where you want to work. And we can add those layers to the map using these map dot etc. functions. And so basically we're telling this mapping panel down here to center on our region of interest, and then we will actually add the region of interest as a layer as well. And you can see that here. Yes, Deanna, I can a little bit. So the directory structure that Deanna is asking about, essentially, if you want to create a new script, you can go new here, and you own your own repository. So this exists at the owner level. And then you can create a new folder, and I'll do that here as an example. And oh no, I do want to create a new repository, don't I? Yeah. So I'll create what I'll call an example repo. And now we'll see that within my users/cjon, there's now a repository called example repo. And it doesn't contain anything. And I guess you could actually put folders within repositories, but I pretty much just work at the repository level. That's probably not best practice. I'm sure someone out there who has better advice on that. But you can add files individually to whatever repository you're interested in. So I'll add an example script to my example repo. And now you can see there is, within the example repo, there is this one example script. And I'll work off of this today so that we can kind of start from scratch. So you can see my example script is completely empty. There's nothing in it. So I'm going to, paste the code. Deanna, did that answer your question? Okay, super. So we can paste the script into our, we can paste the text of the script into our new script and run it. And so we have our centered object with our region of interest. And remember, all of this is run at once. So all of this code I wrote ahead of time, and I kind of banked on it working. So it's pretty helpful to include print statements like you see I have here on line 106, because if things break while you're trying to run your code, you can kind of figure out where that happened. But so we have chosen our region of interest, and now I'm going to define two functions that will operate at the image level. So ultimately what we're going to want to do is we're going to find some Landsat data that covers a long time period. So there's hundreds or even thousands of images that we will work from, and we'll crop down to that. So we're going to define two functions here that operate on individual images, and then we'll apply them to all of the Landsat data that we point to. So this first function is called mask clouds. And like you can see here, it's a function of a single image, and it is going to look within the image for a band called pixel QA. So you might have an NDVI layer, a red, a green, a blue layer, and then we'll have this quality assurance layer as well. And there are two, there's a long story behind the bitwise operators of remote sensing that I don't want to get into too much right now, but if you have questions, we can talk about it later. But what's important is there's 2 bits within the pixel quality assurance layer that indicate clouds and cloud shadows. And we want a nice picture of the ground. We don't want a bunch of clouds in our imagery. So we're going to generate 2 masks here, and those will allow us to remove cloudy pixels from our images. The second function that we're going to use is called add NDWI, which is an index for water. And ultimately, you might want to remove areas that are covered in water from your imagery. So this is a function that takes in an image, and it calculates this water index and adds that as another band or layer onto the image. Okay, So next, now that we've defined our functions and our region of interest, we can start working with some data. So we will create this raw Landsat scene, and we're asking Earth Engine to collect data from this Landsat data product. And anytime you're curious about a product in Earth Engine, you can search it up here in the search bar. And I have quotes, so that's not going to work. But we can see here, okay, so Landsat slash LCO8 slash CO1 slash T1 SR is the Landsat 8 surface reflectance product. So that's, like I was mentioning, you could get a top of the atmosphere layer. This is the surface reflectance corrected product. And we can look at our bands here. And so each image contains, holy moly, like 12, 13 bands, something like that. And some of them are not labeled. So like this aerosol attributes and our pixel QA, which is what we just talked about. There's also bands for ultra blue, blue, green, red. So blue, green, and red are the bands that your digital camera would contain. And then if you have like a fancy NDVI camera, your camera might also collect near infrared data. And then there's some additional stuff that you can look at your leisure. Is there anything else I wanted to say with this? Oh, the other thing is, so if you're looking at these data products, you can also see when the data are available through. So Landsat 8 was deployed in 2013, and the data are available through mid-December of last year. And we can import this collection using, which we have in the code already, ee.imageCollection, and then the data product that we're going to work with. So we've pointed Earth Engine to our image collection, and we're going to say, okay, we really only want to work with data from 2020. So we will filter by date from January 1st, 2020 to the end of December 2020. And that's a little bit beyond what is available, but that's not a big deal. Then we can also filter spatially using our region of interest. And then we will take those mask clouds and add NDWI functions that we defined above, and we will apply them to each image in the image collection. And after we do that, we have this print statement, so we can check out what's going on. So we can look here and we see raw image collection, which is what we printed here. And we can see that there are 40 images that exist within this spatial extent during 2020. And each of them has 13 bands. So there's the ultra blue, blue, green, red, etc., as well as our pixel quality assurance and that NDWI layer that we added on our own. So the next thing that we do is we want to add that data to the map because we want to see what it actually looks like. And you'll notice that when I have this map.addLayer function, I first say raw, which is the name of our image collection. And then we're going to use bands 4, 3, and 2, which are red, green, and blue. And then so everything inside this curly brace is essentially visualization parameters. So it's what do we want to look at? What's the lowest value that we want to map? And what's the highest value that we want to map? And then this last statement, false, means we're not going to add to the map immediately, but it'll show up in this layers panel. And so we can see raw image collection down here is exactly what we added here on line 70. So let's turn that on and take a look at it. And I need to zoom way out, and you'll see why here in a second. So Yolo County actually overlaps with two independent Landsat scenes. So here's a scene here, or maybe it's called a tile. And here's an overlapping tile here. And when we add an image collection to the map, it's only going to plot the top layer of that collection. So this is probably from January in 2020. And you can even see, if you look really closely, there's sort of a line here. And this is where those collections overlap. So artifacts like this are things that we're going to try to overcome with the process that we'll kind of pipeline through here. So now that we have this massive image collection, I'm going to turn this back off to keep the mapping panel open. A few things that we can do. The first thing we're going to do is what's called a reduction. And essentially, this is an Earth Engine operator that takes all of the images in the collection, and for pixels that are aligned in space but independent during time, we're going to find the median value of every pixel that's in this collection. And that is as simple as saying whatever our collection is dot median, and we can print that and take a look at it. So now you can see, rather than an image collection, we have an image that contains 13 bands, and each of these are the median value of all of the appropriate bands from the full collection earlier. And we also added this to the map, so we can take a look at our median raw image now. And you'll see this is still very big. This is not just Yolo County. This is all of the Landsat scenes that overlap with Yolo County. But we've started to get away from that sort of artifact of the line separating those scenes. We can zoom in super close here, and you can see this looks like a pretty continuous image. So the next thing we'll do is we'll take that image and clip it to our region of interest, because we don't want all this extra data. That's a ton of information that you don't want to have to download. And it looks like I actually did not add that one to the map, so we'll come back to that. But what we can also do is extract just our NDWI layer, which is that water index, and add that to the map. And we can see, hopefully here, within Yolo County, now it looks blue because we have water visualization. And if I zoom in super close, you can see areas that are watery are much darker blue. So hopefully this loads in a reasonable amount of time. So this is, I'm not sure what waterway this is, but you can see where wetlands are filled in, they show up as super, super blue. And areas that are less watery, like some of this farmland here, is a much paler shade. So what you can do if you want to remove water areas from your imagery is apply a mask, just like we did with the clouds, using water. And so that pops up here after we've visualized NDWI. We can create a water mask where the water layer is less than or equal to 0. And this will allow us to create a binary watery versus not watery image. And you can see this is our water mask layer here. It can be 0 or 1. So finally, we can remove the water from our imagery if we want, and that we would do by using that update mask function that we also used with the clouds. Or you can choose not to remove the water. Either way, that's kind of your call. But we're going to use some visualization parameters to check out our masks. So here is our water mask, and I'm going to turn NDWI off. And you can see these are the areas that are flagged as watery. And ultimately, I was interested in also including watery areas in my image. So you can see that here in our RGB including water. But if we took the land only layer and plotted that, it's underneath. So I'm going to wait till it loads here. If I remove our full data set, you can see there's like a see-through area here. Now it's easier to see. And so we have masked out those watery pixels. But if you're interested, you can retain your water by not masking it. And for the sake of continuity in the image that we're ultimately going to produce, I keep the watery pixels in. But I included that in case people wanted to take water out. So we have our RGB Landsat imagery, and you may have removed water if you chose to. And let's see what else. We have it, ultimately, we have finally cropped it. We used that clip function, so it's only within Yolo County or whatever your region of interest is. We include our visualization parameters, and we plotted it to take a look at it. Now, a couple things to note. Where are the visualization parameters? They're right up here on line 101. If you wanted, the, these are relative values, and depending on what scene you use, like if you use the desert, everything will be very bright. And so it'll change how the image actually looks because you're mapping these remote sensing values to what a monitor understands. And this starts to get back at that GitHub or the Stack Exchange post that I shared earlier, because ultimately what you're doing is you're mapping red, green, and blue to values between 0 and 255, because that's what a monitor understands for displaying red, green, and blue images. So if we wanted, we could change this max value to 3000, and we can take a look and we'll see everything looks a lot darker now. Or we could change it to 1000 and everything should look super blown out. Yeah, and so that's obviously unacceptable. You can't use this in a presentation. The 0 to 2000 numbers are values that I came up with through tinkering. But the nice thing is what you see in your map for this final RGB including water layer, that is what you will download. So we're going to have some time to play around with this in a couple minutes. And I would encourage you to run the code and plot your map and see what it looks like. And if it's too dark, try changing these visualization parameters here. You can change the lower bound and the upper bound. So depending on what your ROI is, that could have a big effect on how things actually look. So we have all these layers that are added to the map. We've masked out our water. We've actually applied a visualization scheme to it. And what we ultimately want to do, because we want to map this using R and ggplot, we need to download the data. And we can use this series of functions that are in the export family to essentially send this data product to your Google Drive account. And there's a series of parameters that you have to define here. So you say what your image is when you're exporting an image, and you need to give it a description because in this tasks pane over here, you want to see what you're actually working with. And I created a map time folder in my Google Drive account. And then you need to define, I'm going to skip scale for a minute, the region of interest that you're actually working in. It seems redundant to me, I'm sure it does to you as well, that you would define the region after already saying what the image is. But I think it might be useful if you have a much larger image and you want to just export a smaller region. But the important things here are the scale and max pixels parameters. And so I want to take a minute and do some back of the envelope math. If you are using this for a presentation, the highest resolution that you could really reasonably want to work with is working with a 4K display, which is like what they use in movie theaters. And a lot of TVs these days are 4K for whatever reason. It seems overkill to me, but I'm sure there's somebody out there who thinks it's better. But a 4K display has 3,800 horizontal pixels and 2,100 vertical pixels. So there's really no reason to include 100 million pixels within your image if ultimately you're only going to be able to display 8 million pixels at its best. So when you're working with Landsat or Sentinel or whatever data, and you want to create a map like this that you can use in a presentation, it's important to think about your final product first. So you need to think about where you want to work, how big your picture is going to be, and what that means for how many pixels you want to export in the first place. Because there's no reason to export a 10 gigabyte image only to plot it in R and cut it down to 400 kilobytes. So 3,800 times 2,160 is just over 8 million pixels. So there's no reason to set your max pixels on the export to more than 10 million pixels. If you do, you're going to end up with files that are huge. They're going to take forever to download. They're going to take forever for Google Earth Engine to even process. And you're just kind of shooting yourself in the foot. So let's see, what am I missing here? Scale. So this line defines the actual scale of the pixels that you're exporting. And so I use 90 here. So a 90-meter pixel is approximately, I think that's the width of a soccer pitch, isn't it? I'm not sure. You can imagine 90 meters. So a single pixel in one of your images is going to be that wide unless there are more pixels than the max pixels, in which case there will be some downsampling that happens. And then finally, I also exported the region of interest to my Google Drive because I want to use that perimeter to make my ultimate plot much more beautiful. And you can see if we go back to the context maps repository, I have a border around my Yolo County ROI, and that makes a nice clean exterior that everybody appreciates. Okay, so once we have gotten to this point, we have a cohesive script that can be run, and we've already, or at least I've run it for illustrative purposes, but I'm going to do it again just to make sure everything works. Once again, we have these different images that we printed out, but then over here in the tasks pane, it has YOLO ROI, which is our region of interest, and then YOLO Landsat 8 RGB 2020 surface reflectance. And when we run these, it will give the option to send these products to a folder in the form of a shapefile. I'm not going to run it now because I already have. And similarly, we have 90-meter pixels that are going to be sent to Drive in the same folder. So all of that yeah, Alex, thanks for pointing that out. So there's a bunch of stretch parameters that you can use to choose how to define your highest and lowest values for Earth Engine exports. I have not used any of those like native Earth Engine stretch functions. I've done a little bit in R, and I know you can do a bunch of that in ArcGIS too. As far as the export scale resolution versus native scale resolution, yeah, that's a great question. So when we're exporting data, Landsat data comes at a resolution of 30-meter pixels, but depending on the size of your region of interest, it would be ridiculous to use 30-meter pixels. For example, if you wanted to plot all of California, and you wanted to have your pixels be 30 meters by 30 meters, you would need like a bajillion pixels, and your file sizes would be huge because California is so big. And so it makes sense to use a larger scale in your export because that will end up making the pixels that you spit out much bigger in space. And Earth Engine by default uses a nearest neighbor interpolation function. So if you go from a 30-meter pixel to a 90-meter pixel, Earth Engine is going to ask, okay, there are 8 neighbors around this series of 9 pixels. How can I best choose a sort of classified version of the pixel to represent this larger space? There's also a form of interpolation called bilinear interpolation, which I much prefer for continuous data. Nearest neighbor is better for categorical data, but Earth Engine has nearest neighbor as their default. But what's important here is that this scale is a larger value than what the data product comes in. So if you have like MODIS data and you have a 500-meter pixel, if you specified your export scale as 90 meters, Earth Engine would give you a false impression, or the resulting data product would give you a false impression of high resolution data because it would have these 90-meter pixels, but they would have come from a 500-meter pixel. So it basically splits something into blocks and assigns those values to all of the blocks, when in reality, you don't know how the sort of sub blocks that you created are distributed in the data. So yeah, I would suggest having this scale parameter be equal to or larger than your native product resolution, and making sure that you don't have a scale that's so small that you're going to be super confusing when you try to export it because you have such a big region of interest. Okay, so we can go back up to the top here, and there's this region of interest that I defined for Yolo County. And like we used an image collection before, for our Landsat data, there are feature collections in Earth Engine that contain basically our vector data. And so this Tiger census data contains county shapes. So if you wanted, you could export data that is not for Yolo County, but instead for Mariposa County. And we could do the same thing. And now we'll see, oh, we're looking at not Yolo County, but Mariposa County. There are numerous other shapes available. So you can use entire states, which you can see down here. One thing I forgot to mention was that in Earth Engine, because this is JavaScript, hashtags are not comments. 2 forward slashes create a comment. And a forward slash with a star followed by a star with forward slash makes a comment chunk. So down in here, starting at line 11, there's a couple other example regions of interest you might want to choose. So you could use the Tiger States product and find just Hawaii, or you could use the EPA ecoregions and pull out the full Sierra Nevada. Naomi asks, what happens when you run the median function on an area that has snow during part of the year? That's a great question. The data filtering that we used here does not remove snow. And in red, green, and blue capacity, snow is very bright. It's essentially white. So you'll get really high values for those. And that will persist through your median reducing. So one option would be to add another line in your mask clouds here that specifies the snow layer, because the QA layer also has information on snow. So we could say bit 4 needs to also not be flagged. But for me, I like to include snow because the intention that I typically use for these maps is just to get an audience acquainted with where I'm talking about. And so if I have a map that contains the Sierra Nevada, I want there to be snow in that map, because this is not like an analytical GIS map. This is just plotting a space in red, green, and blue colors to get an audience familiar with where we're talking about. Let's see. Okay, so there's a few questions in the chat. Let me just finish up introducing the ROI thing, because we're going to have an open work time, and then I'll get to those 2 questions. So you can choose whatever ROI you might be interested in. So we have the Sierra Nevada, we have Hawaii, and you would essentially replace this line 8 and 9 to be those ROIs. And then ultimately you'll be asked to, do you want to export these in the same capacity? So with that, I would like to take maybe 20 minutes and give people an opportunity to play around with the code, choose their own region of interest, and download something that they can work with in the R section, which will start at, let's say 20 minutes. And so that would be 11:08. And we can start the R section, which I'll live code and work through, and that should be pretty quick. So if you are comfortable checking out this script and tinkering with it, you should go nuts. And in the meantime, any and all questions are welcome, and I will start to address the questions that were asked in the chat in order here. So, oh, on the note of the export, Alex asked about, can you mention how to finish the export? So in my experience, I've used the run button, and then simply click run once the task is brought up. And I'm going to add a B so I don't overwrite something. And that will ultimately begin the processing, and you'll see it has a little counter here. and you can check the status with that question mark button. And ultimately, those will end up in the drive folder that you specified. Okay, so just to hit Sam's question first, because I have a feeling several people will be interested in this. You can import your own area of interest if you want. You would need to go to this Assets tab in the left pane, and you can create a new table upload with either shapefile or a CSV, depending on how your data are defined. And you will select some source files of whatever you're working with. I'm glad nothing embarrassing popped up there. Add it, give it an asset name, and upload it there. That usually takes a little while. So if you want to add, an asset, you should hop on that immediately because it does take some time. Okay, let's see. So to go back into the questions, hopefully people that are feeling independent at this point can go ahead and start playing around with stuff. Naomi, I think I answered your question about the median reducer. Leah asks, is there a way to look up or print a list of all the counties in the code? I'm thinking of counties that may need state codes attached to them somehow. Yes, like Jefferson County in multiple states. I'm sure there's a way to print all the counties available, but I would recommend almost kind of figuring it out on your own. So we can look at this Tiger Counties feature collection the same way that we looked at our Landsat raster data. And you'll see under the table schema, there's a name called name, and that's the county name. And so that's how I pointed Earth Engine toward Yolo County and Mariposa County. And thankfully, there's only one of them in the US. But if you want to be more precise, you can use what's called the FIPS code. So you would have to look this up, but it's as simple as Googling. So you can look up YOLO FIPS, and you'll see the state and county name and the FIPS code. So if we went to California and YOLO, and I put this code in here, I think it was it county FIPS? Let's see. County FP. This would give us, hopefully, uh-oh. What did I miss? CLUNTYFP. Well, I did that right. Yolo County FIPS code. I know I've looked this up before. 06113. Well, I'm not sure why that's not cooperating. Let's try this. Nope, didn't like that one. Okay, let me come back to that and answer a few more questions first. So if you want to be precise, I'd recommend trying to use the FIPS code, or what you can do is say filter to the state level and say we only want to use California or whatever, and then filter to the county itself. Ellie, you can use two counties together by using a filter and function. So I would recommend going into the docs and then EE filter, and check out the EE filter and, so you can use more than one county that way. Let's see. MJ asks more about the cloud mask, which I know I didn't get into super detail about that. So there are a few different ways to mask clouds. A lot of remote sensing products come with estimated cloudy pixel percentages for a whole scene. So you can say, I only want Landsat scenes that are less than 30% cloud cover or something like that. But what we're working with here operates at the pixel level. So every pixel has a cloud shadow estimate, a cloud cover estimate, a snow cover estimate. And again, that you can check out using your Landsat product up here. So we can look at bands, and under Pixel QA bit mask, there's cloud shadow, snow, and cloud. So if you want to remove snow, you can also add a 4 here. So we have mask 1 is for bit 3, which is our cloud shadow, if I remember correctly. Mask 2 is bit 5, which is the cloud itself. We could add a mask 3 here and say that bit 4 needs to be equal to 0, and then update the mask again with mask 3. And so adding these lines of code would also mask snow out if you really wanted to. And again, that depends on what your ultimate goals for this are. Let's see. The way that it works, so this is being mapped to all of the images in the image collection. So we have not, at the point that we apply the function, which is here on lines 60 to 64, we have not clipped the data to the region of interest yet. We've only filtered the image collection to include images that overlap with the region of interest. So all of the cloud masking is happening for all of the pixels in all of the images that overlap with our region of interest. But this, you could change the order of these things, where you would say, okay, we have an image collection that is, this is all of the Landsat images that exist. And we could start by mapping this mask clouds function, but that would be really inefficient because you're going to mask clouds from Japan only to ultimately filter down your image collection to Central California anyway. So when I'm doing this, I start out with my filtering options of filter date and filter bounds, and then I start masking because you would do so much unnecessary masking anyway that it would be computationally really expensive. As far as affecting temporal resolution, if you want to get time series data, you are not going to want to do this median reducer. If you want time series data, you're going to have to export a series of images in the form of temporal bands or an image collection, and there's code out there to do that too. It's beyond the scope of what we're working on today, but if you want to talk more about that, shoot me an email, because there's a lot of good code out there for that. It's just not something that we can really deal with today. Floyd asks about Landsat gap filling. Landsat 7 is a big pain in the butt. I'm sure that there are answers out there for dealing with that. And I thought I saw Alex said something about it. Okay, yeah, so there is code, Floyd, that you can see Alex included there. Namely asks if we need to do a download now to work on the next part in R. If you want to work with your own region of interest from some other county or some other, like an ecoregion or a state, then yeah, you'll need to download now. But if you don't want to wait on your download to complete or whatever, you can also access the same data that live in my context maps repository. And you can access that using the data folder. And then there's a couple other examples in here, but what you'll ultimately, or what I'll be working off of, is this YOLO LCO8 RGB 2020 SR, which is what I just showed you how to export, and then also the YOLO region of interest shapefile, which is this series of 6 sort of subfiles. So yeah, if you want, you can download directly off of GitHub using the download button, or you can download via Earth Engine and Drive. That is up to you. Now, let's see if I can figure out this FIPS issue. Nope, that wasn't it. So once again, if you are working on your own data, we'll reconvene at 11:08. In the meantime, I'm going to try to figure out what the issue is with this FIPS stuff. And keep the questions coming, because I'm paying attention to that too. Marina, I have not used histograms on Earth Engine before. I'm not sure exactly what your question is about.
Christian, I just had a quick comment. This is Marina.
Mhm.
You said that the mask takes a long time to implement if you don't do the filter bounds. I haven't had that problem. I always clip afterward. The only time that I found that it takes a while to load is if I'm zoomed out very far. But I don't apply a filter bounds before doing a clip, and I haven't run into runtime issues.
Interesting. I thank you for that. I'm not sure, that might be a product of the power of all of Google's computational stuff, because who knows how many computers they have tied together.
Yeah, it won't show the image in the viewer if
Mhm.
you don't do that as filter bounds. But depending on how far you're zoomed out. But as long as you clip it before you try to download that image, obviously, if you try to download the entire world, then it'll definitely cause issues. But yeah, I haven't run into that problem. It just won't load the image unless you're zoomed into the correct, to a close enough range.
Sure. Oh, that's interesting. It looks like it's almost 11:10 here already, so I would like to reconvene. Oh, Ryan asks about the Sierra with the requested payload size exceeds however many bytes. This is because the Sierra ecoregion is it has a lot of features, and Google doesn't like having to process things with lots of like vectors with a lot of points on them. So what you can do, Ryan, and if anybody else runs into this problem, let me start sharing my screen again. I have in the past had to deal with this, and it's a little bit circuitous, and I can't tell you exactly why it works this way, but if you specify for your region, if you do ROI dot geometry and then parentheses and then dot bounds, this will pull out just the exterior of that region, and you will not run into the payload size issue anymore. I don't have a perfect explanation for it. I'm sure it has to do with processing and what Google wants to do. Alex says it doesn't like the number of vector nodes, but yeah, so this, if you add geometry.bounds after your region for image exports, that in my experience has overcome, I think, all of the export issues. So yeah, if you use the export geometry.bounds, that will just do basically your extent window. And you've already masked out the things outside of your ROI anyway. Okay, so at this point, hopefully people have managed to download a GeoTIFF and a region of interest from Google Drive. So for me, that looks like here in map time, you can see I have all of these different GeoTIFFs that were generated with Earth Engine, and then their associated ROIs. And I'll be working with, again, the Yolo County one and the surface reflectance product. If you struggled to get to that point, you can, again, download that material directly off of the context maps repository that we're working with. But the next thing we'll want to do is start working in R. So you can, sorry, I'm looking at the chat. Michelle included a link to the data, and Alex points out that you may have to simplify your geometries when uploading to Earth Engine as an asset if you want to use your own shapefile, because sometimes, yeah, the number of points in the vector gets confusing. I have put together a full script for already plotting these maps, and I had originally planned to live code this, but the script is already online anyway, and I think I would rather just work off of that and walk everybody through it, and then you can tinker around with it as you please, and we can have a little conversation then for more questions. So the first thing is I failed to mention in the email that Michelle sent out that you'll also need the cowplot library as well as the scales library. And I don't think scales is pre-built into R. So you can use install.packages, cowplot and scales if you need to. I'll put an example in the chat. So if you need to install those, you can go ahead and do that too. So the data that we've downloaded, I have saved in a subdirectory called data. But when we use raster data in our, we need to point to the file path that that raster data set lives at, and same as with vector data. So we can start out by loading our packages. And again, all of this code is available on the context maps repository under scripts and plot maps SR, which I'm now putting in the chat. So you can download that, copy and paste it into an R window, whatever you want to do. And if you are in Windows, or if you don't have a working directory set, you may have to point to a different location for your data. This might be under, for example, downloads, depending on what folder you have your data saved in. But once we've loaded our libraries, we can import the image using the raster stack function. And it looks like I don't have something set up right. I'm not working in a working directory yet. So I'm going to set my working directory. And now I should be able to load my image. Okay, great. And I can look at the image and we'll see that we have a raster stack that has 3 layers, and those layers are our red, green, and blue layers that we generated with that visualization function in Earth Engine itself. And the layers are called viz.red, viz.green, and viz.blue, and they're mapped to the values between 0 and 255. So a pixel that's completely white would have 255 for red, green, and blue, and a pixel that's totally black would have 0 across the board. That's going to be important here in a moment because if we, let's see, documents, map time. If we actually look at the data set we're working with, you'll see anything outside of your region of interest is black. And that can be nice depending on what kind of an aesthetic you're going for, but I prefer a white background. And so we're going to work with this a little bit and basically remove all these black pixels and end up with something that is much brighter to look at ultimately. So we can import our region of interest in the SF library of functions, which is a spatial vectors manipulation package, and we can take a look at that. And once again, this is also in the same projection information from our imagery, which is going to be important because they need to overlay. And then, as Alex mentioned, you're also going to need USA boundaries, which contains the states, and we can filter that using pipes to look at California itself. And that's a multi-polygon. Okay, so once you have your image, your region of interest, and then maybe a contextual California shape, should you want it, we can start to actually do some data wrangling. And if you're familiar with the tidyverse, there's a function called fortify, which converts objects into data frames. And we need our data to be in data frame format to use it with ggplot. And in the RS toolbox library, there is a sort of version of Fortify that allows us to take raster data like our image and turn that into a data frame. Now, you may recall that we set our maximum pixels on the Earth Engine export to be 10 million. For now, I'm going to set this as 1 to the 4th, which is just 10,000. So this is going to look like a really grainy image ultimately, but it's going to save us in some processing power. I am sharing my screen, right?
Yes.
Okay, thank goodness. That would have been horrible. So if we set our maximum pixels here within fortify to 1 to the 4th, which is 10,000, this should fortify pretty quickly. Okay, so that's already run, and we can look at that. And you'll see that we have now, rather than a series of raster layers, we have a data frame with columns for X, which is our longitude, Y, which is our latitude, and then those 3 layers, viz, red, green, and blue, which indicates what our pixel values are at each X, Y coordinate location. So we can once again use some piping to go from this full fortified image to data frame object. We'll pipe it to a rename function because it's nice to just use R, G, and B from a simplicity standpoint. And if all 3 of those are 0, we're going to remove them, because remember, if all 3 are 0, that means that it's a black exterior pixel, which is irrelevant to what we want to map anyway. So if red plus green plus blue equals 0, we know it's outside our region of interest. And then finally, what we need to do is rescale each of these 3 columns to go from 0 to 1 rather than 0 to 255, because ggplot expects raster cells to be on the scale of 0 to 1 rather than 0 to 255. So when we run this data pipe, we can take a look again, and you'll see that we now have our X and Y as we did before. We don't have any R, G, and B where all 3 equal 0. And the scaled versions of those are, rather than 0 to 255, they are on a scale of 0 to 1. So next, it's helpful to have some element of context for your region of interest. I think that the map makers out there would frown upon my lack of a north arrow and scale bar. But again, if you're using this for a presentation and you're presenting to your department at the UC about some county in California, for example, people generally know which way is north in Yolo County and how big Yolo County is. So I create an empty ggplot object and then add a layer for our California spatial layer, and an additional layer that contains our region of interest, and then remove all the X and Y axis stuff because it's a map, not a graph. And we can take a look at that and we'll see, okay, I accidentally imported the Sierra Eco region rather than Yolo County, but you get the idea. We have California and our ROI highlighted. So I'm going to go back and do this with Yolo rather than Sierra because it's smaller. Now if I run this again, yeah, you'll see we have just Yolo County, little old Yolo County highlighted in gray. So the next plot that we're going to create is the really complex one. And this, once again, will start out by creating an empty ggplot object. And then we will use this function geomTile to add essentially a raster layer to our plot. And the nice thing about geomTile is that we can independently specify our data set from other vectors. And we can use this RGB function to define our fill value. And RGB allows you to create a hue based on, well, a hue and saturation and value as well, but based on our scaled red, green, and blue values. So for example, I could type RGB 001, and we would get 0000FF, which is blue. David asks, why not use geomraster? You can do that too. I forget, I know there's a reason that I didn't use geomraster for this, and it might depend on the spatial extent. If you're working with a small region of interest, there's not a dramatic difference in the size of the northernmost pixel and the southernmost pixel. But if you're working over broad geographic areas, the top of California would really actually have a different resolution than the bottom of California. So the way that it maps on I think can be slightly affected, but ultimately geom raster is a version of geom tile. So yeah, like I said, I can't remember exactly why I used geom tile. It might have something to do with this fill argument. But it's worth playing around with. Try geom raster and see what happens, because the worst thing is that it might not work. Yeah, so we'll define our fill as this red, green, blue combination of our different layers. And you need to use this scale fill identity to specify that this is how we want to plot it. And then we'll also overlay an empty version of our region of interest to add that border that we were talking about. Finally, we can, once again, use this theme void to remove axis labels and stuff. And then I made the plot background transparent. So we can take a look at that, and we'll see a super grainy version of YOLO County. And remember, we only set our max pixels to be 10,000 because right now we just want to take a look at what this looks like. We can use our 10 million pixels once we know that it looks how we want it to. So now we have an idea of what YOLO County is going to look like. We've already created our contextual county in state shape, and we can combine them to make a complete context plot. So we can use cowplot's ggdraw function, which generates an empty drawable plot. And we'll add our RGB plot, which is the one we're looking at right now, alongside our vector plot, which will just be in the lower left quadrant. And if we run that, we'll ultimately see, okay, so we have our RGB, our California vector, and this looks something like what we want it to look like. So now that we've tested it, we can add 1E8 here instead to be 10 million pixels and run the whole thing again. And this might take a couple seconds. But once it's completed, we can take a look at complete plot. And once it's done thinking, there we go. We have a high resolution view of YOLO County alongside California with a little contextual county outline. So once again, recall that we have all of these limitations on our 4K display. You can use the ggsave function to save precompiled ggplots. So we have the RGB plot only, which is basically this, but without California in the lower left corner. And then we also have our complete plot, which contains also the California little contextual element. And you can define the size of your output plots. So I did 7 by 7 inches at 300 pixels per inch because a 4K screen has 3,800 horizontal pixels and 2,100 vertical pixels. So 7 times 3 is 21. So we have ultimately a 2,100 by 2,100 pixel plot, which is about as tall as you could want your output to be anyway. And we can save this and then take a look at what we spit out, which lives in here. And that was, let's see, YOLO RGB SR, which is this one. And look at that, it's 709 kilobytes. This is less than a megabyte image that is as high resolution as you could hope to display to your audience anyway. So hopefully this functionality will allow you to use high quality contextual RGB imagery from your satellite data and get it into a format that you can put in a presentation and not eat up a ton of file size unnecessarily. Okay, it looks like there's a few questions in the chat. So Deanna had trouble with getting the library remote sensing toolbox loaded but not installed. That might be a bug that we have to deal with. Oh, Michael, thanks for pointing out. Yeah, ggsave is super nice because I will often, you might have noticed that in the code, I have the actual plots hashtagged out. That's because it takes a long time to render the graphics on the screen, and I already knew that they were going to work. So what you can do is create your plot and assign it to an object, and then leave it be. And then after the fact, just save it, because it's much quicker than waiting for R to render it. So the last thing I'll say is that this is pretty generalizable. You just need to be careful with what max pixels arguments you use, what scale your pixels are at, and try to think of your end product before you start downloading data, because you know that you're limited in screen size anyway. So it's silly to download the full resolution Landsat data or the full resolution Sentinel data when you're only going to use an interpolated subset of it anyway. The nice thing about the approach that we use here is that you can define when you're interested in. So what we used in our example script was all of 2020. But if you really wanted, you could say 2017 to 2020 and get 3 years of imagery. Or you could say 2020 0701 to 2020 0731 and only look at July of this year and things like that. So another thing that you'll find in the scripts folder of this repository is get data by monthly median. And that allows you to generate monthly median estimates of the red, green, and blue values across the year. And ultimately, if you use that and then this plot months script, you can convert 12 monthly images into a moving GIF that would look like this. So that would be a grand challenge that maybe if you want, you can work on now or sometime in the future, or in the context of your own work. But yeah, so at this point, I just wanted to take the remainder of the time so that folks could play around with stuff and try to get things working on their own, and answer any other questions that you might have. Alex, I have not used the RGEE package at all. In fact, I haven't even used the Python version of that. Leah, if you're having a problem with Fortify, try specifying that you want to use RS Toolbox. So, oh no, that's not true, because it won't recognize it as. I don't think that this would work. No. Are you sure that you have RS Toolbox loaded with library?
So I was just saying that if anyone else is having that error, for me it was the ggplot2 package version. So if you upload or upgrade ggplot2 to the latest package version, then it should work.
Oh, super. Okay.
So while people work through the end of this and have questions, I think what I'd like to do is just thank Christian for this fantastic workshop. And I will stop the recording so you guys can ask all of the questions you might not want to ask on recording. So thank you, everyone. I'm going to go ahead and stop this now.